Okay, thanks very much for the opportunity to participate in this important conference and to speak here. So what I'm going to talk about, and just before I start the talk, I would like to apologize for the few people who heard this talk once, twice, or more. There will be just small additions this time. Okay, so the problem I'm going to talk about is a joint work with Hans Lindblad. And let me briefly go through the motivation for the starting point of the problem I'm going to discuss. So many years ago already, there was the issue of how to prove asymptotic stability of coherent structures. For example, solitons. So this is really my starting work with Michael Weinstein since I came to Princeton. And at some point, about 15 years ago, I think, we tried to do the kink problem. So, but we were humbled down by the dispersive part of the problem. And so then about 10 years ago or more, I started all over again. And now there is a solution for a small part of the PDE part, which comes from the general kink stability problem. And that's what I'm going to talk about. And so you'll see which part I'm looking at. So the starting point is the equation dt minus Laplacian. This is in one dimension, so this is just dx squared, okay? Plus m squared, which I will take to be 1. U is equal to a function of u. So f of u, if f of u, for example, is the sine or the cosine function, then we are talking about Klein-Gordon equations where it is known that there is exact solution as the kink solution. The kink solution is a topological soliton of the simplest type. Namely, it has a constant value which are different at plus and minus infinity. You can ask the same question about what happens in 2 dimensions, and I will make a comment about that later. What happens in this? Okay, so, but in general, you may have other nonlinearities that you would like to deal with. All right, so now the starting point for the method that we use to prove asymptotic stability is to linearize around the kink solution. So the structure of the kink solution is not going to be very important for us now. So I will call it K. It's just that it is smooth and it looks like that. And then if you just linearize around it, then you will get an equation of the following type. A remainder term, which behaves like there will be some k, maybe k squared, maybe some higher power of k. Let me just write k squared for simplicity. So there will be k squared r plus some k tilde r squared plus some k prime r cube, and so on. All of these k's are powers of k. So they are smooth function, and in fact, either they look like that, or they look like a C0 infinity function or exponentially decaying smooth function up to a constant. So if you subtract the constant, you will get, for example, here, the quadratic term and the cubic term. So these terms in general, you can think of them as a C0 infinity function plus a constant, or exponentially decaying function plus a constant, and so is this one. So now the problem is how to prove a dispersive estimate in global existence for this kind of an equation. So R is small because R is the perturbation on top of the K, and we want to assume that we have a small perturbation of K. So R is small, and we can assume that it is nice and smooth and compactly supported at time 0. And K is of order 1, but otherwise nice and smooth. So the question is how to prove scattering and global existence for this problem. So there are 2 situations. First of all, let's look at the linear term. This linear term we can put here, and then it acts like a potential up to a constant. Now, there are two possibilities. Either this potential removes the zero energy resonance of the Laplacian in one dimension, and then the problem is much easier, or it doesn't. When it doesn't, then the behavior of this system is like t to the minus half, even at the linear level. The decay is t to the minus half. So I'm interested in this case. I'm interested in the case where the decay is t to the minus half, and that this term doesn't help you. So in this case, I don't know how to do the problem in the linear case. So I'm going to drop this one. Okay. So then we are left with this one. This one, I only know how to do constant. So we will put here alpha 0. Yes?
Quick question. So in the case where there is no zero energy resonance, then everything is going to be OK?
Not everything is going to be OK, but sorry.
So in the case when K, I guess, whether there's a zero energy resonance depends on the particular form of the nonlinearity.
Yes, it depends on the kink or vortex or whatever.
Right. But suppose you don't have a zero energy resonance, which means that the decay rate, I guess, the local decay rate is like t to the minus 3/2 in one.
Right. So in this case, life is better. So the type of terms that I will be dealing with will not make trouble. So the problem will be maybe at some other levels, but not at the level that I'm going to talk about. Okay. So here I will put a constant term. I think this term will still be a problem, but the kind of problem that I'm going to discuss will disappear. And for this problem, I'm going to take a constant plus some localized C0 infinity function R cube. So this is the function. So all of the work I'm going to talk about is on the effect of this term. In the case of a resonance. And as you will see, of course, this kind of a term is generic, not just for this problem, but in general, I can add to practically any nonlinear equation small non-homogeneous term, and the coupling constant will become a function of x. So it becomes variable coefficient. So the problem I'm going to talk about is what happens when you add beta of x r cubed to the equation. Okay? And as you will see, even though beta of x is a C0 infinity function, hell will break loose because of this term. All right, so let's go to the next step. So here's the theorem. So the theorem is that if you start with this problem, with alpha 0 constant, beta 0 constant, beta of x is compactly supported, initial data smooth, compact, and small in high enough Sobolev norm, then R in L infinity will decay like a constant t to the minus half. This constant depends on the size of the initial data in some norms. In fact, I'm cheating here. It's not even that. It is 1 plus rho to the 1/2. And rho is t squared minus x squared to the 1/2. And we are only looking at the region where t is larger than x. Okay? So this is the main result. Now, this is exactly the free behavior. So the question is, what is the problem? I mean, if you can, in the end of the day, you can prove global existence and get that the decay estimate is the right one, then what is the issue? So first of all, as you will see, the proof is very different from what was done before because of this term. And secondly, the proof also shows that the solution of this equation do not preserve some sort of regularity of the original problem. So what happens is that this equation, you can define, you can construct all kinds of invariant norms, invariant Sobolev norms. And these invariant Sobolev norms will remain bounded, so they are in fact constant with respect to the free flow. And if you add this term and this term, you can show that they remain bounded for all times. However, as I will explain later, because of this term, these invariant Sobolev norms actually grow with time to infinity. All high powers will actually grow to infinity with time. So this phenomena is similar to weak turbulence, except that now it is happening at the level of the invariant Sobolev norms and not on the level of the original Sobolev norm. So what would be a possible consequence of this is, I'm not sure, but it could be, for example, that when you have a quasi-linear equation, then the growth of the invariant Sobolev norms make it impossible, say, to prove global existence even. So. OK, so how the proof goes. The first step is to remove this term by normal form transformation. You have to realize that this is a necessary thing to do, because if r decays like t to the minus half or rho to the minus half, then this term is like a potential which decays like r to the minus half times r. So it decays like t to the minus half times r. T to the minus half is not integrable. That's why it's very long range, and that's why you have to remove it. Okay? So the way this is removed is by a similar method to what Chatat did when he introduced the method of normal form transformations to PDEs. So what you do is you introduce, in this case, a quadratic bilinear form, which is pseudo-differential, and you use that, and you construct this kind of bilinear transformation so as to eliminate this term up to cubic terms. Okay? So I will not go into the details of this procedure in this case. I will just tell you some of the technical things which are necessary to do from now on because of this process. So the bilinear form in this case is of the following form. It is a bilinear function which looks like that. 1 over rho to the 1/2 times b1 of v plus 1 over rho to the 1/2 b2 of v dot, where v dot is dv dt, and b1 and b2 are bilinear pseudo-differential operators. So you take these two expressions, you stick it into the equation, and you choose the expression for the b1 and the b2, or in fact the kernels of b1 and b2, to be such that it cancels out the rho to the minus half decay terms on the right-hand side. There are many terms. Many of them are higher order, but the ones which survive, you use the b1 and the b2 to knock off. So you get a nice, in fact, you get a nice pseudo-differential, elliptic pseudo-differential operator. It has nice properties. However, when you have a nonlinear equations, you have to choose a norm where you want to close the whole equation. So the norm that we would like to do is L infinity together with H1. But we find out that we could not really show that this transformation is good enough in these norms, or at least we could not control it in H1. So we had to introduce a slightly stronger norm as well. So we controlled it in terms of 3 norms, except that the third norm is a Bezov type norm that we have to introduce. And then from now on, every estimate has to be done, in fact, in terms of these 3 norms. So let me just write it down here so that you will appreciate my pain and suffering. So this is a projection on all frequencies less than rho of v in L infinity plus a sum over all dyadic frequencies lambda, which are larger than rho, So, and of log of lambda over rho absolute value times the projection on frequencies at a shell, at dyadic shell lambda, V also in L infinity. Okay? So from now on, you have to estimate everything in this thing. So the price you pay, this is nonlinear equations. So the price you pay for this is that you have to control the action of this kind of projections on a nonlinear term. Nonlinear term is a product of functions. So this doesn't commute through the function. So you have to break every function into low frequency, high frequency, and mid frequency. And then you have to combine the terms and look what is the leading term and what is the higher order terms, and throw the higher order terms and keep the leading terms and so on and so forth. There is a name to it in French. It's called paradifferential calculus. But that's basically what you have to do here in order to deal with the nonlinear terms. OK, so you do that. And now the next step is following, in fact, a method that Hans and Lindblad and I developed more than 10 years ago, how to deal with the constant coefficient case. So we had a method which eliminated the need to do normal form transformations for this term. And for the quadratic term, it was possible to reduce the problem to an ODE normal form transformation. So it was much simpler. However, it fails when you have this kind of a term, and I will explain why. Okay? So this method starts by switching to hyperbolic coordinates. So if it was NLS, we did it also for NLS, and then you have to switch to conformal coordinates, and you can do similar things. Okay, so hyperbolic coordinates. So we introduce hyperbolic coordinates first, and then, so we have rho, which I introduced already. It's c squared minus x squared to the 1/2. And then you have to introduce another variable, y. And basically, I will say that x is rho cosh hyperbolic y. All right, then you write the equation in terms of the new variables. So you get box in the hyperbolic coordinates plus 1 becomes d rho squared minus 1 over rho squared dy squared plus 1. So what is the idea? Why it is good to work in hyperbolic coordinates? Well, you can see it from here, and that was the basis of our previous work. You have here a factor of 1 over rho squared. This 1 over rho squared means that this term is short range, because it's integrable. Of course, it will be integrable only if you can control dy squared. You have to show that dy squared is not blowing up on you. But dy squared is a high-frequency problem. And it is believed, at least from linear theory, that when you have a long-range problem, the long-range problem is a low-frequency problem. It's not a high-frequency problem. So you would expect that this term is higher order, and you can drop it and later try to prove that the dy norm is bounded. Now, you have to control this in L infinity, which means that you have to take one more derivative, at least, of the equation, and then do an H1, estimate. If you try to do it even in the constant coefficient case, you discover that it doesn't work, that you need to take one more derivative at least, and sometimes more. So you can take many more derivatives, and you estimate them in H1. And in this way, you get a good estimates on this one, and you can bootstrap the whole thing together by using the assumption that this term is higher order. Everything closes perfectly if you have constant coefficient terms. Why this method fails? Well, first of all, taking the derivatives with respect to dy is a very similar idea to what you would do with the quasi-linear equations. You apply more and more powers of the invariant Sobolev norm. dy is an invariant Sobolev norm. It defines an invariant Sobolev norm. So why does it fail when you have this term? Well, let's see. So now we take this, and we write the equation over there again using these variables. So we get d rho squared minus 1 over rho squared dy squared plus 1 v equal to f, and f v cube over rho, and v beta of rho y v cube over rho. And if there was a quadratic term, it would be over rho to the 1/2. Let's assume I eliminated it. So here is the cubic terms. Okay, so that's the leftover. Now, if you look at the cubic term, if you try to apply derivative with respect to y to the cubic term, this factor, each time the dy hits this function, you get a factor of rho coming out. So then after one step, you cannot do it anymore, basically. Right? Even if beta is nice and smooth, doesn't help. Right? So that breaks the methods. Okay. All right. So, okay. So now, in order to skip many formulas, I just tell you in words that the way you prove estimates for this kind of an equation is you apply derivatives to the equation and maybe some weights, and then you write down the H1 estimate, the energy estimate, the basic energy estimate for the derived equation. And this way you get estimates, and you try to use all of them to close. Of course, you have to use also Sobolev estimates along the way because you have to control L infinity, for example. And remember, I am hiding under the rug the fact that every single estimate also has to be done not just for L infinity and H1, but also for this one. Okay. So, so if I am to believe that the long-range problem is a low-frequency problem, then I should only look at the low-frequency part of the problem. And the way I'm going to attack this problem is by actually eliminating this term. Mainly, I will focus on this one. This term I know how to deal with, even without normal form transformation. But this one I don't. So I want to eliminate this term by a normal form transformation. That's the plan. Okay? However, if I am to believe that the long-range problem is coming only from low frequencies, I want, first of all, to project on low frequency the whole equation. Now, this is a nonlinear equation, so there are some there are some problems to deal with, and there is a price to pay when you do such a thing for a nonlinear equation. Nevertheless, that's what we do. So we project on the low frequency part, and the question is, why is it that the low frequency part is the only place where there is a problem, as far as the long-range problem is concerned? So to see why, so let me introduce again this frequency projection. So this is a projection on Xi less than lambda, and but everything is dyadic here. So, okay. And then observe that if we project on any function u on frequencies larger than lambda, then it is bounded by, and suppose we want to control u by h1 now, right, in L infinity. So what happens? In one dimension, I lose half derivative. So this gives me lambda to the 1/2. But I can control the function in h1. So this is one full derivative. So I get a gain of half derivative. So this means that I can control this by lambda to the -1/2 times u in h1. So this is another way to see, right? And this is important for understanding why things work, is that if you project on high frequency, and if you can control the h1 norm by bootstrap argument or whatever, then the high frequency is small. It's not relevant. So what are we going to do, in fact, is to project V. We are going to project V on frequencies less than rho, and call this, say, V1. That's, by the way, it's pretty high frequency, right? It goes up to rho, but it's not more than that. OK, so using that, you see that if I project on frequencies which are less than rho to some power sigma, then I will gain a decay in rho. So if you have a decay in rho, this is a higher order term, so you don't have to worry about it. Okay. All right. So, okay. So now we do all that. We do all that, and now let's focus on the simplest problem where we are already doing this projection. So the problem now is the following. We have d rho squared minus 1 over rho squared dy squared plus 1 times some function w is equal to beta of rho y over rho times the projection on frequencies less than rho v cube plus higher order. So that's the new equation. Now what is higher order? Of course, you have to compute the projection on low frequency of v cube minus the projection on v low frequency cube. So there are a lot of terms there which are intermediate. Okay, so let's ignore that and worry about only the leading term. So that's the leading term. So the way to deal with this is to introduce some kind of a normal form transformation, except that the standard approach to normal form transformations of bilinear or cubic pseudo-differential forms did not work. I mean, for us, it did not work. So we actually introduced a new type of a normal form transformation for this kind of problems. So it looks like that. So you choose W. So I call this W2 in the sense that this is the leading order behavior of this equation, and it's not the exact solution. So this is a normal form of the following type. We take functions fi of rho and y times a polynomial fi in v1 and v1 dot, where fi is a polynomial of the following form. Fi of v dot is defined as v to the power 3 minus I, v dot to the power I. So this is the type of normal form transformation that we try to use. And we also put some kind of pseudo-differential conditions about these functions fi, which are we want to construct or find. So the next step is to take this ansatz, plug it into this equation, and just equate all the terms of order 1 over rho on both sides, at least formally behaving like 1 over rho, and so that the leftover is decaying faster than 1 over rho, and therefore we don't have to worry about it. Okay? So what does this give us? So this gives us a system of equations for the fi, which depends on the beta, on the function beta of rho. If I make the simplifying assumption that the fi are function of rho times y, then I will get a system of equations for the beta which are only of a function of one variable. Therefore, they are a system of ordinary differential equations. So in this case, if you take fi to be rho times y, then you will get a system of 4 ordinary differential equations. They are linear. You can solve them. And when you solve them, you see what is the behavior of the solution. Okay? So, all right. So let's okay, save you the computations. And so let me write down, first of all, what is the equation that you get in case when fi are functions of rho and y. So you conclude that what you have to do is the following. You have to choose fi of rho y minus f double prime I of rho y acting on the polynomial fi plus fi of 4y fi squared equal to beta of 4y f0. And from this, you conclude that you can find, so this gives you a system of linear equations for the fi, and you conclude that you can choose f1 equal to f3 equal to 0, and f0 double prime plus 2 f0 minus 2 f2 is equal to minus beta of the corresponding one variable now, z. And f2 double prime plus 6 f2 minus 6 f0 is equal to 0. So you get a set of two coupled equations. So these equations are the equations for the coefficient functions fi in the ansatz. So if we can solve it and we can find nice functions, then we are okay. So now you just diagonalize this 2 by 2 matrix and you find the solutions. And after you diagonalize, you write down two linear combinations, G0, which is 3f0 plus f2, and G2 f0 minus f2. And then you get G0 double prime is minus 3 beta, and minus G2 double prime plus 8 G2 equal to minus beta. So very simple equations, right? So you just take Fourier transform and you solve them. So I did all this algebra to show you where the problem is coming from. So here is the problem. This equation is singular. This equation is singular because if you now take the Fourier transform, you will get that G0 hat of xi is minus 3 beta hat of xi over xi squared. And you get something similar from here. What do you get from here? G2 hat of xi with a minus xi squared plus 8 G2 hat of xi is minus beta hat of xi. And this is telling you that G2 hat of xi is beta hat of xi, or maybe, yeah, over what? 1 xi squared minus 8, or maybe the other sign. So now you see what is the problem. There is one resonance frequency, which is 0, and there is another two resonance frequencies, which are plus minus square root of 8. So this is where the problem comes from. Okay? This is telling you that the leading order behavior of the solution of this equation is not nice, because these functions are bad. Right? The other terms are higher order, so they should not cause too much trouble. So how much time do I have?
You've got about 12 minutes.
Okay. All right. So in fact, now just the fun begins in this problem, because now you have to find a method to control the solution by going around these singularities. So, all right. So what do we do? Well, we have to do a completely different type of analysis for the 0 frequency problem and for the square root of 8 frequency. So for the 0 frequency problem, here is what you have to do. This is a resonance, so you cannot really, so this is how the system behaves, so you cannot just transform it away or something like that. That's it. That's what it is. So how can you get an estimate? All right. So of course, this singularity that you get here is only if beta hat of 0 is not 0. Right? Otherwise, there is no singularity. Similarly, if beta hat of square root of 8 plus minus is 0, then also there are no singularities. But of course, you cannot assume this on a general coupling constant. So we assume that it happens. So then the idea is the following. The idea is that in the case of a zero frequency resonance, what you do is you break this function, beta hat, and you write it like that. You write the function beta as an infinite dyadic sum of beta j's, where each beta j has frequency in a dyadic interval 2 to the minus j beta. Okay, so now you see for each beta j we have now a coupling constant which does not have zero frequency problem. So we can construct a normal form transformation for the problem which contains only a beta j. We can solve the problem for this one, and we can compute an estimate for these fi's for each value of j. Now you have to add up the pieces. In order to get an estimate for the original equation, you have to add up the pieces. And the reason that you can add up the pieces and don't lose as you approach, as j goes to infinity and this interval approaches 0, because all the estimates deteriorate when j goes to infinity because the frequency approaches this point. So to compensate for that, you use the fact that under our assumption, beta is a smooth function. And therefore, beta hat is nice and fast decaying. And therefore, these projections actually gives you extra decay in the L infinity norm. So you get an extra decay. Each such term has an extra decay in L infinity in powers of j. In fact, you get 1 over j, I think. So this is what allows you to take the sum over j over all these terms. Okay? So that's how we take care of the zero frequency problem. Right. So the other problem is more serious. The square root of 8 problem is more serious. That doesn't work anymore. And I cannot give you all the details, but I can tell you what you have to do and what has to be done. So the square root of 8. So what you have to do in this case is you, first of all, have to replace the ansatz back again to rho and y. Because when you look into the details of this extra singularity square root of 8, you see that in some sense they are more serious than the zero frequency one. But on the other hand, they live only finite time in some sense. So how do you use that? You use that by replacing this ansatz by this ansatz. And then you plug this into the equation. And then you derive equations for the fi. The equations for the fi in this case become hyperbolic second-order equations. So you get 4 hyperbolic equations. Okay? I will write one of them. Box hyperbolic of f0 minus 2 f0 minus 2 d rho f1 plus 2 f2 is equal to beta of rho y. And there are 3 more. And you drop the terms which are higher order, whatever that means, by computing what is the leading behavior of such terms. And you get 4 equations which are linear, but hyperbolic this time. In other words, they are PDEs. You do something similar to what I did here before, and you are able to diagonalize this matrix and to find the behavior of the solutions, and what you will find out that the solution is indeed singular. There is a singularity at square root of 8 plus minus, and you have to deal with it. And the way you deal with it is you go back, you plug it, you plug this back into the equation, and like the linear equation, and you ask, what is the behavior of the solution in the presence of this singularity to leading order? So what we did is to use the explicit kernel representation of the solution of the linear equation acting on this singularity. And then you have to do stationary phase analysis near the singularity and away from the singularity in order to estimate the H1 norm. And what you get is that you can control these functions just with one derivative, which is needed to close all the equations. So that's how one proves the theorem that I originally described. So now I want to show you a little bit that was done after that. This is sleeping.
Oh, this is mine.
Lighting. Lighting. Projection only. Overhead projection. Okay, so this is the normal form. Well, it's supposed to move.
Oh, the advance?
It's not moving.
Oh.
Okay, this is summary of. So here are the 4 hyperbolic equations that you get in the case of the square root. And as you can see again, you are left with a simple linear problem to solve. And what you do is you have to use the actual kernel representation for this operator. In fact, to the inverse of this operator applied to this function. And this is how you find the singularities of the normal form transformation. So what is this? So I believe that this phenomena that adding this small localized perturbation in the long-range case creates weak type turbulence in the sense that some invariant Sobolev norms are growing is a general effect. It's not something specific to this problem. Okay? So I asked a student to do the numerics for nonlinear Schrödinger equation with the same term. So you take the nonlinear Schrödinger equation and you add a localized term, which it appears in every experiment in principle, but of the u cube and the u squared terms, and ask what happens to these invariant norms. So the invariant Sobolev norm for the relevant one for Schrödinger equation is x minus the derivative times t. That's x minus the velocity times time. This is supposed to be constant as a function of time under the free flow. And in fact, this is a fundamental estimate in scattering theory. You prove that x minus vt remains bounded in some sense. That's how you prove scattering theory in a non-trivial situations. Okay? So here, what you see is what happens to this quantity to the power 6, expectation to the power 6, as a function of time. So these two lines here are when you take the free flow and the usual NLS. But when you add variable coefficient, that's what you get. Okay? So it's clear that this is a general effect. Okay. All right, let me stop here.
Questions?
So going back to the original problem, the kink problem, so there's the linearization has a, what is it, a k squared, or it's the kr squared term.
Yes.
Right, where k is the...
Kr squared is quadratic, yes.
So can one, so what happens to those terms?
Yeah, we
And
are
can
working
one
on
take
it.
advantage of the monotonicity of the k,
No.
or?
We are working on it in the case when the coefficient is C0 infinity, for example. And the resonances in this case are much more severe. And when you do the normal form transformation of the type that we introduced, you get terms which are formally higher order, but it's not clear how to control them because they are still quadratic and they have two derivatives extra in them. So they are quasi-linear. So we don't know yet how to, even formally, how to deal with it. So the quadratic terms with non-constant coefficient are more serious problem. I mean, I'm not saying that it is not doable by similar methods. I'm just saying that it's more serious. And it will show up with the Schrödinger case just as well. Schrödinger case is much worse, because in the quadratic case, the absolute value make it impossible to take derivatives, because the nonlinearity is not even smooth in this case. So even in 2 dimensions, I believe you'll see these problems, because in 2 dimensions, you have a vortex, which is the analog of the king, and you'll have similar problem.
Other questions?
I have one. So how about the problem in 2 dimensions, but I wouldn't allow you to change the quadratic coefficient to a constant and the linear coefficient to a constant?
Yeah, if the quadratic term is non-constant coefficient, then it will be a problem. It is long range in 2 dimensions. So you'll have the same problem. I mean, in some sense, it is a weaker problem because the decay is 1 over t, it's borderline. So.
Right.
But still.
But you're still looking at kink in one direction and flat in the other, or which coherent structure you want to linearize around?
No, if it is kink like that, you will not get this beta of x. You will get something else. You really have to look at the vortex, for example, in 2 dimensions.
I see.
Not a kink.